So again, I haven't completely caught up. This warm-up question is meant to be a review/challenge question, and I'll cover the material for it in the first few minutes of class, but go ahead and start thinking about it. I'll set it up in just a second once everyone's here. Meanwhile, I'm happy to announce I'm pleasantly distracted. I just checked my email, and NSF just gave me a $2 million research grant to take our labs and expand it to a national curriculum. So very excited about that. But I'll try to stay focused on lunar phases instead for the next 50 minutes or so.
That's awesome. Congratulations.
Thank you. I'm very happy.
So where would the national curriculum expand to exactly? Like other colleges?
Other colleges, yeah, it's meant to be an undergrad curriculum. Some high schools use it. It's already been adopted by a dozen universities. And this semester that seems to have doubled because everyone's in need of online compatible labs. So we're at 2 dozen already. This was supposed to build us out to 3 dozen, but we have 5 years to do it, and I imagine we'll have even more than that. But it's not just to expand it. You know, there's money for instructors to learn the curriculum, but also to carry out surveys. If you're in our lab courses, you're probably going to be hit with some pre and post surveys. We're trying to evaluate things like how do the labs impact not just learning gains, which is what people traditionally study, but student attitudes, self-efficacy, career intentions. We'll have site visits to the various institutions. It should be the largest study of robotic telescopes used for education ever done, which is pretty cool. And I'm not an education researcher, but I partnered with some of the best, and they're in the team, and they're going to be doing the work. So should be fun. And there's some money in it for my group, and so I get to keep paying the salaries of my programmers, and that's always my key thing. Anyway, we are at 2:40. So let me set you up with this warm-up question. In the last class, I set up the warm-up question, and I forgot to get back to it. So I remember to get back to it this time. So let me explain this, particularly to the first years. You may not be familiar with this UNC tradition, Cosmic Cantina. How many of you have been to Cosmic Cantina? Probably sophomores, juniors, and seniors. Yeah. Good burritos, really inexpensive, and no, they didn't pay me anything to say that or to put up this warm-up question ahead of time. I think maybe I should go knock on their door and let them know that I pitch their place to hundreds of students every year. Maybe I can get myself some free burritos. But anyway, you go there, it's on Franklin Street, or just right off Franklin Street. They have 2 murals, one on the east wall and one on the west wall. And the one on the east wall is a mural of East Franklin Street, and the west wall is a mural of West Franklin Street. And on the west wall, they've drawn the moon. So in case you're trying to figure out what that is, that's the moon. And so the question is about what time of day it is. And don't try to base it off the color, you know, the shade of the sky or anything like that. The walls are yellow, and they just pick colors that work well with that. Base it off the moon, where it is in the sky. It's low in the western sky. And its phase is, its phase is full, because we can see the whole thing. And given that, you should be able to determine that in these murals, it's either 1, an hour or so before sunrise, 2, an hour or so after sunset, 3, an hour or so before sunrise, 4, an hour or so after sunset. I won't give you the time now to think it through. It's just you have in the back of your mind, and we'll cycle back through. We're going to talk about phases of the moon next, and then this problem will hopefully become a little bit easier if it's not immediately obvious. Okay, so let's see, lunar phases. Let's get some slides going here. Let me back up. Okay. Well, just phases in general. Excuse me. Let me move this, make use of the dock cam a little bit, slide it over. So here we have a picture. This is a picture of both the Earth and the Moon. It was taken by the Galileo spacecraft on its way to Jupiter back in the 1990s. And the reason I put this up here is to show that it's not just the Moon that has phases. When we talk about phases, we usually think of the Moon, but any object out there in space, spherical object in particular, can have a phase. And it depends on just two things. If we talk about phases, it depends on the direction of illumination, and it depends on the direction of viewing. Those two things. You know, as we look at this particular picture, the sun is clearly off on the right. It's illuminating the right-hand side of both of these worlds. But given the angle that we're looking at it, what phase would we call this? What's the term for this phase? Anyone want to venture a guess?
The last quarter?
Yeah, quarter. Quarter. It could well be first or last. Normally first and last refers to the Moon and its orbit around Earth, but just in terms of the shape, quarter is the answer. Sometimes people say half, sometimes I say half, because it looks like it's half illuminated, but technically the word is quarter, because we can only see half of it, so half is a quarter. So these are quarter illuminations, quarter phases, but it depends on the direction of viewing. If we view it from this angle, it's a quarter. If we were to view it from off on the right, like in the classroom, I'd walk off to the right side of the classroom and stand by the screen so you could better visualize it. But imagine I'm standing over there somewhere by the sun looking at this. What would I see in that case? What would the phase be for both of these objects?
Full.
Full. Yep, we call that full. If I'm standing on the other side, I'm looking at both of these and the dark side of both. What phase do we call that?
New.
New. Yeah, so full, new. We have quarter phases in between. And let me just see what's next. So yeah, next I'm going to demonstrate this. I think you get the idea. And again, the point of this is phases can be on any object. It just depends on these two phenomena. I'm going to turn the camera around here and go back to my demo table. I still got the light there representing the sun. In this case, I'm going to be the Earth, and I'm going to hold up the Moon here. So the styrofoam ball is the Moon. And normally, you know, if we were in class, I'd bring up some volunteers to do this, but I'll just do it myself here. So if I stand in this configuration, so I'm Earth, here's Moon, there's the sun. Again, you're all seeing this from the side, and so you're probably seeing some type of quarter phase. A phase that's pretty close to quarter. But from where I'm standing, what phase is it?
New.
New moon.
Now I'm going to let it orbit around me, and it orbits counterclockwise as viewed from the top. So the Moon's now over here. I'll let Earth rotate a little bit so I can look at it. And I'm seeing pretty much the same thing as you now, quarter illumination. It's not super dark in here, so it may not be super apparent. In the classroom, I can get it really dark, but not so much here. Now, if I come over here and stand just a little bit out of the way, because if I stand in the way, it's an eclipse, right? And that's a whole different topic. I'll stand a little bit out of the way and I look at that phase, and what do I call that?
Full.
Full, yep. And then over here, it's quarter again. Now back to your comment about first quarter and third quarter. This first one here, this first quarter. So you go new, first quarter, full, third quarter. Okay. And of course, you know, if I did games like blocking my view, then I'm having eclipses of one type, or if I let this be in my shadow, that's an eclipse of another type. Those don't have, every time we have a new moon and a full moon, we don't have an eclipse. It's a little bit more subtle. The plane of the moon is tipped, as we'll learn. We'll come back to all that in the next class. Oh, I forgot to mention, by way of announcement, as you all know, there's no class on Monday. Monday and Tuesday have been canceled, so you can go home for those who are still in transit. And we're required to make up the class. And the way I'm going to do that is, instead of trying to find a time that works for all of us, which will never happen, I will give you a recorded video at the beginning of, like, the first lecture in lesson 2 is a fun lecture. I talk about Stonehenge because I have some expertise there. We do some archaeoastronomy the entire time. I'll probably give that to you by video, and you can watch that separately. It's a fun lecture, so even though it's not live, since it's a fun topic, I'm hoping you'll be able to watch it. There's a homework question on it, and that's how I'm going to make up the class. But on that note, the homework's been moved till Friday, just because we've lost yet another day. So homework 1 is due on Friday. Okay.
I have a question.
Yeah, go ahead, please.
Where do waning and waxing gibbous fit into the
That's my
moon's phases?
my second to next slide, so I'll get there in just a second. This slide basically shows what I just did with the styrofoam ball, except here it's a baseball. We have a new phase, we have first quarter, full, third quarter. But then, as you just asked, what about these other terms, waning and waxing, crescent and gibbous? Now, I'm not going to test you on the terminology here, but it's good to know what it is, where it comes from. So here's the moon in the new phase. You know, the sun is way over here somewhere. And so we're looking at the dark side of the moon. We call that the new phase. And as I was just hinting, the plane of the moon's orbit's tipped a little bit. And so it's not always perfectly lined up. Sometimes there's a little sliver of light, maybe over the top or under the bottom. It's rare for it to be completely blocked. When it is, we have an eclipse, and that doesn't happen every new moon. Anyway, you might have a little sliver of light during the new moon, but you won't see it. And why don't you see that little sliver of light during new moon? The new moon is next to what in the sky? What object is right there when we have a new moon?
The sun.
Sun, yeah. And so if the sun's right there, it makes the sky bright. You can't see the new moon. But if you wait a day, you can see the crescent moon. So as the moon moves a little bit from the new moon configuration over in this direction, you'll start to see a crescent, just a little bit of, it's between new moon and first quarter, you get that crescent shape. In fact, anyone see the moon last night? Last night was one day past new moon, so we had this perfect crescent, thin, wispy little crescent. Even if you didn't see it last night, I'm sure you've seen it before. You've seen a really thin crescent moon, and it was just hovering above the horizon, right before, around sunset. That's because it's close. It's still close to the sun in the sky. The only way you're going to see that really thin crescent is once the sun gets below the horizon, and then you have that crescent moon that you can see until it sets. So there's just a brief window there, and it was really nice looking last night. Anyway, term waxing, so crescent refers to the shape. Waxing means it's getting bigger. So we have a waxing crescent all the way to first quarter, and then when it's more than a quarter, we call it a gibbous. And here it's a waxing gibbous because it's still getting bigger. I used to have a Cocker Spaniel many years ago, like a black and white party mix, great dog, but near the end of her life, she went blind, and she was okay with that. She didn't do anything after that except eat, but so, she got fat and kept getting fatter, so we'd call her waxing gibbous. She didn't seem to mind as long as I kept feeding her, but yeah, waxing gibbous, the moon is more than one quarter, and it's just getting bigger and bigger until you get full moon. And then it's waning. Waning means it's getting smaller, so we have a waning gibbous, third quarter, waning crescent, and back to new moon. So that's where those terms come from. Okay, again, I'm not going to test you on it, but now you know. Now, this is the God's eye view, being up in space over top of everything, looking down upon it, and it's the easiest way to understand what's going on. But we don't have that privileged view of the system. We're down here on Earth. So what's this look like from the Earth point of view? And this is actually another exercise that I want you to do. There are these two long, I've given you a couple exercises. One is to go out and sketch the northern and southern skies a couple hours apart. One is a long-term, all semester long, monitoring how high the sun is in the sky, how long the day is. This is the third observing exercise. And this takes place pretty much every day over a 2-week period. And since yesterday was just one day after the new moon, we can start this today. if you're willing. If not, you can catch it next cycle. But this is, I know you've seen the moon out there in the sky at night and during the day. Have you seen the moon during the day? Some of you? And it's a misconception because the children's cartoons, they simplify it too much. They say the sun's up during the day and the moon's up at night. And that's not the case. The moon's up at night half the time and it's up during the day half the time. It's always going around. Just sometimes a little harder to see during the day. So, but it's there. You've probably seen it. Anyway, you've seen the moon out there in space. You've seen all these phases, and there are different angles between the sun and the moon. And you've probably never put it all together. And the point is to do that now. You understand it kind of intellectually. So the way this exercise works is you go out at sunset. It's a 2-week exercise. I'm not going to make you do the other 2 weeks because you'd have to get up for sunrise to catch the moon for that. But sunset, you go outside. If it's clear, find the moon in the sky. Now the sun will set in the west. And if it's near new moon, like last night, the crescent moon will be really close to it. So if you go right at sunset, you'll see that crescent moon hanging above the western horizon. But each day, the moon is getting farther and farther in its orbit. And after 1 week, it's first quarter and it's 90 degrees from the sun. If you put one arm pointed towards the west and the other arm pointed towards the moon, but keep it on the horizon, first quarter's at 90 degrees. And then it keeps getting even more and more. We get into the gibbous. Eventually you get a full moon, 180 degrees apart, opposite side of the sky. So when the sun is going down, the full moon is going up. And then it keeps working its way back around in the morning sky until you have a new moon again. So the exercise if you go to the ebook and go down to Lunar Phases, again, you can skip all these UNL links that I believe are broken, but here's a description here. There's another worksheet. And this is 3 columns, 7 times, and then it just repeats over here. So you go out, write the date and the phase. Maybe skip the first one since we missed yesterday. Maybe we can fill that back in a month from now. But put the date here and the phase, sketch the moon, and estimate that distance on the horizon. Is it right next to the sun, 0 degrees, 45, 90, 3, or 135, 180? And soon you realize there's this correlation between phase and how far away it is from the sun. The other thing you may notice, I'll bring the dot cam back here, is that the phase of the moon always points towards the sun. So, like last night, the sun had just set. Here it is below the horizon, and the crescent moon was nearby. And it's like an arrow pointing to the direction of illumination. Even if you're in the gibbous phase, let's say here's the whole moon, and this part is illuminated here. It's like a fat arrow, I guess, pointing towards the sun. So even if the sun's not up in the sky, it's telling you the direction to the sun. Anyway, I want you to go out and actually observe these things and see these connections. And that way it's not just an intellectual exercise. For the rest of your life, you'll notice these things and you'll say, oh, there's the sun over here, the moon over there. It's got to be this phase at that angle, that kind of thing. Again, in ancient days, everyone knew this stuff. It's just in the modern era, there's so much else to do and think about. We don't understand the basics of how the sky works anymore. So I want you to go see it. Now, yeah, go ahead.
So my family is Chinese, so we celebrate holidays where the full moon is like extra bright and extra big. Why does that happen?
Yes, so as we'll talk about probably next class, as we're talking about annular eclipses and things, the moon's orbit is not perfectly circular. In fact, I'll just jump ahead and bring up a slide because it's in our deck coming up here. There it is. The moon's orbit is not perfectly circular. Sometimes it's a little bit closer, and sometimes it's a little bit farther away. And when it's closer, it appears bigger, and when it's farther away, it appears smaller. No, this is not the psychological effect. Many of you have looked at the moon, say, oh boy, it looks big tonight, or oh no, it looks small tonight. That's a different effect, and I'll tell you why that is. It's because your brains are broken, and I'll explain the effect and prove it to you. But it really does look bigger and smaller because it's closer and farther away. And so if you have a full moon when it's also big, and we call it a supermoon, and that's probably what you're referring to.
Okay, got it. Thank you.
Sure. Let's see where we were. We were here. Okay, so this is a good time to go back to the warm-up question, which I've described. And, here's the same picture as before, just a little bit harder, black and white. That's the moon. And I'll go over, let me slide this over a little bit. We have 27 responses. So basically, low in the western sky, we have a full moon. So what time is it at Cosmic Cantina on Franklin Street? Always, because the mural's permanent. Appear to be about 75-ish of you. So definitely try to put something in. Try to get it up in the 40s. If you fail, I'll put you in breakout rooms as punishment. Social interaction will be punishment. Okay, looking pretty good, mid-40s here. You can keep voting, but let's take a look at the answer. Show values. Histogram. Ooh, it's like a three-way tie, which means time for social interaction punishment. Let me see if I can remember how to do this here. Breakout rooms, and let's see. We have maybe 4. Maybe I'll do 20 rooms. It's 2 to 3 per room. What if I did 15? That's 3 to 4 per room. Let's do that. 15 rooms. I'm going to create the rooms. I'm going to send you in. I'm going to clear the board. And so once you've come up with a solution, go ahead and post it and then come back. Okay, the rooms are open. So as you come back, go ahead and post your new answers. Everyone will be back in about 7 seconds. Okay. Now, a lot of those wrong answers could be people who gave it a go before we covered the topic. But now that we've covered the topic, hopefully it's easier to figure out. And I think we had 44 responses before, so let's try to get to a similar number.
I already want to change my second response.
Well, if you all do poorly, you'll get a third chance. So, all right, let's see here. Show values. I think it's looking a little bit better. Show histogram. Yeah, most of you went for 1, which is the correct answer. So, anyone want to explain why it's the correct answer? Anyone bold enough to do it?
I guess I'll go.
Do it.
So the full moon always rises in the east and sets in the west, and in this case it is setting in the west. It's directly above the horizon.
Yep, that's half of it. So if it's a full moon setting in the west, where's the sun?
It should be rising in the east.
That's right. If the moon, the full moon is 108 degrees opposite the sun. So if the full moon is setting, it means the sun is getting ready to rise.
Yeah, that's it. So
Yep. And so that means the answer is number 1, an hour or so before sunrise. So that's what time it is always at Cosmic Cantina. Okay, good. Hopefully that was interesting. And let's move on from lunar phases, unless there are burning questions. And we'll talk about the lunar month next. Okay. Lunar month. Oh, I have one more phase picture that's kind of fun. This is a picture of the moon, crescent phase. It's almost about to become a new moon. So just a wispy, wispy crescent. But if you look carefully, I'm not sure how well it comes over the Zoom connection. Things are a little bit fuzzier. But if you look here, there's another object with the exact same crescent. Anyone want to venture a guess as to what that is?
Is it Venus?
That's Venus, yeah. Venus is kind of the brightest planet, and it has about the same configuration between the sun, the direction of illumination, and the Earth, the direction of viewing. So you have the same phase. Again, this is just to emphasize it's not just the moon. Any object can have a phase. You can
I have
see.
a question.
Yeah, go ahead.
So the moon, how did you know that the moon was before sunrise in the previous question? Like, could it have also been after sunrise?
It was before sunrise because and I think I have the clock here. If it's a full moon, they're 100% opposite. So 180 degrees opposite. If it's a full moon, when the moon's up, the sun's down. When the sun's up, the moon's down. So since this moon is getting ready to set, that means the sun is getting ready to rise.
So the full moon is not visible in the day?
That is correct. That is correct.
Okay.
Now, there's a little special case.
Confused because I feel like I've seen it in the day before.
No, you'll always see it just as the sun is setting. It will be coming up. Now, the sky will still be bright around sunset for a while. So you may see the rising full moon in a sky that's not completely dark. Because if the sun is just a few degrees below the horizon, you still have a relatively bright sky. And there's a second effect that boosts this called atmospheric refraction. Everything near the horizon is pushed upwards visually. As the light's trying to come through our atmosphere, it boosts it up. So you can get both the sun and the full moon above the horizon just for an instant, though it's a technicality.
Okay, thank you.
In general, you can think of them as opposite. Okay. Lunar phases. So I'll put that slide up there, but let's go to the dot cam. Let's see, I'll make the slide big. Dot cam over here just for right now. So, or not lunar phases, but the lunar month. We just did lunar phases. And the lunar
Are you
month,
still there?
I am still here.
I bet he blue screens. Oh, he's here. Whew.
No, I'm here. Can you hear me?
You froze for a second.
Okay, yeah. I already had my blue screen on the first class. It only happens once every time. So I think in the future, I'm just going to start these things up a couple of hours early, get my blue screen out of the way. And anyway, I'm here. Okay, lunar month, there are two ways to define it, sidereal and synodic. We've seen the term sidereal. No, I'm here. I'm here. I swear I am. Can you see me? Can you hear me?
I can hear you now.
Okay, good. It says my connection's stable. Let me just check, make sure I'm on the right one here. Yeah, it's as stable as it's going to be for me. So, two definitions of the lunar month. Sidereal, that's a term we've seen before when we talked about the sidereal day, and that was with respect to the stars. And this is the sidereal month, again, with respect to the stars. How long it takes for the moon to go completely around the Earth back to the same orientation with respect to the distant stars. And that's something we don't notice. We don't see the moon in this constellation, and then a month later we see it back in that constellation. We don't notice it because the moon is bright. And around the moon we can't see the stars because the moon's so bright. But it's the true orbital period of the moon. And then you have synodic. This is tied to the phase cycle. This is the one that's easier to see. Full moon to full moon, a quarter moon to quarter moon, or new to new. So this diagram here kind of illustrates it. It's a lot like the diagram we saw before about the day, except this is the month. So here we have Earth, we have the moon between the sun and the Earth, so it's a new moon in this configuration. And then the moon's going to go around once with respect to the stars. So the moon right now is in this part of the sky, and over here it's in that same part of the sky. As we talked about, since the stars are so far away, these two angles are looking at the same stars, even though Earth has shifted a little bit. So the time to go completely back around with respect to the stars, that's 27.3 days. I just wrote on the dot cam. I'll bring that back up in a second. But you can see, since Earth has moved in its orbit a whole month, about like 1/12 the way around, that means the moon is no longer between the sun and the Earth. It's going to have to orbit a little bit longer to get back between the sun and the Earth and give us another new moon. So the synodic month, the phase cycle, is a little bit longer. It's 29.5 days. I'll bring up the dot cam so you can see that. And that's the one we see really easily, the synodic, even though the true one is the sidereal. Now, the calendar month is 30 or 31 days, with the exception of February, which is 28, except on leap years when it's 29. And it's clear what they tried to do is they tried to take our calendar and break it into lunar chunks, but it just didn't break into a nice clean number of integers. So they padded the months with a few extra days. And so the days, the months of the calendar are like the synodic month, but with a little bit of extra time for all the months except February. That means you can actually fit 2 full moons in the same month. If you had a full moon right at the beginning, you can have another full moon right at the end. It's rare that it works out that way. And when you do have that, we call that a blue moon. Ever hear the phrase once in a blue moon? It means something that's rare. And that's something that is rare, having 2 full moons in the same month. You can't have 2 full moons in February. February is too short. So if you ever hear once in a February blue moon, which you'll never hear because I made it up, but that means never, right? But once in a blue moon means rare. Okay, let me ask you a question. Does the moon rotate? We know it revolves. We know it orbits. Does it also rotate on its axis?
No, it's locked to
No.
us.
It
Those
does,
tidal
but
lock
it's
is called,
same
right?
at the same speed it revolves around Earth.
Yeah, so I heard a number of things that were wrong and right at the same time. I was hoping some people would say no, and because that's what most people think, because we always see the same phase. But you also said because it's locked to us, and that's the reason why the answer is yes. So let me show you some figures to hopefully clarify that. This is from a different textbook. This is the case if the moon was not rotating. So here we've painted one crater red and a crater on the other side blue. So if we start with new moon, the red craters face towards us, and here the moon is orbiting, but in this case, which is not reality, we have no rotation, which means by the time it would get to the other side, we'd see the blue crater, we'd see the back side of the moon every 2 weeks, and then we see the front side of the moon. So given that, then your answer is yes, the moon is rotating. And right, do you agree? You see it now? But it's rotating at exactly the same rate that it's revolving, that it's orbiting, which means this red crater in this case is pointed towards us, pointed towards us, pointed towards us, pointed towards us. The same side of the moon is always pointed towards us. It makes people think the moon's not rotating from our point of view. But if you go out there in space, yeah, it is rotating. It's rotating the same rate that it's revolving. That's why we always see the same side. And that may seem like a really wild cosmic coincidence. Why would that occur? But it turns out almost every moon in the solar system rotates and revolves, spins and orbits at the same rate, such that one side always faces the planet. It's something called tidal locking. It's something we'll study in great detail in the later lessons of this course. But basically, the gravity of the Earth is so strong it squeezes the moon. The moon's gravity squeezes the Earth too. That's what gives us our tides. But the gravity of the Earth is so strong it squeezes the moon from a circle into like a little bit of a potato shape. I exaggerate greatly. It's so little you can't see it in pictures looking at it, but it does a little bit. And then that elongation wants to point towards the object it's orbiting around. It's the lowest energy configuration. So the moon is squeezed out a little bit, and then the orientation of that squeeze naturally settles, pointed at the central body. So all the moons get tidally locked. The rotations match their revolution, with a few weird exceptions, chaotic orbits of a few moons. Okay. And, okay. Any questions about the lunar month? And we'll get into eclipses then.
Yeah, sorry, what's the definition of the sidereal month again?
So the sidereal month again is the amount of time it takes for the moon to go around the Earth back to the same position with respect to the distant stars. Synodic is with respect to the sun, and since Earth has moved, the moon has to move a little bit farther to get back to the same synodic position, the same phase position. But sidereal is with respect to the distant stars. It's shorter. Okay, eclipses. Let's talk about eclipses. Let me ask you a question or two. My first question is, what is the orientation? We have three objects, right? Which one's in the middle for a lunar eclipse?
Earth.
Earth.
Yep. It helps that I kept flashing the slide ahead of time by mistake. But yeah, there it is. Sun's off to the left, Earth in the middle. Earth casts a really big shadow. The moon's a small object, so it moves through that shadow. Again, this is not to scale. The moon's much farther away, where the shadow's been tapered a lot more. And it only spends about 100 minutes in the shadow. Have you ever seen a lunar eclipse, total or partial? Yeah, they're not too infrequent. And I don't know, it makes for a good date night. It's always on the night side of the planet that this happens, so it's a good date night event kind of thing, you know. Get a blanket, bottle of wine. It's worked for me anyway. So, yeah, that's lunar eclipse, about 100 minutes. And before we go to the solar eclipse, let's look at a few things with lunar eclipses here. So this is a time sequence. You'll see these whenever there's an eclipse. Photographers take these time sequences. You'll see them on the internet. And there are a couple things that you can extract from it, including one thing that's misleading that I want to explain. But first, what can you extract from this? If you look at the shadow on the moon, so the moon's moving this way into Earth's shadow and then out of Earth's shadow. See the shadow here? Is that a straight line or is that curved?
Curved.
Curved. That means Earth is
Round.
round. Yeah.
Round.
A sphere.
Yeah. And so you may have heard, like, before Columbus, everyone thought the Earth was flat. And that's not true. We've known all the way back, ancient Greek times, the Earth is round, just from this shadow it casts on the moon. So this, I hate to even bring it up, but flat eartherism has become one of the new pseudoscience topics. We live in the post-fact, post-truth era where people can believe whatever they want to, and it's put on some kind of level of equivalency with facts and well-thought-out, reasoned arguments. Anyway, flat eartherism is just goofy, and you can see it right here from the shadow. If Earth was flat, this is the shadow it would cast on the moon. And so lunar eclipses don't look like that. And there are about a zillion other ways to dispel it too, but it's not worth our time. Well, the biggest advocate was Kyrie Irving, and he played basketball for Duke, so you can kind of understand that. Anyway, I got my little Duke dig in there. Had to get that in. Anyway, what else can we learn from this sequence here? Well, when you look at these eclipses, the moon is moving into shadow, darker, 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 and then you see this picture where it's bright again all of a sudden, and then it moves out. And this isn't reality. It's not like once the moon moves into Earth's shadow, it's suddenly bright and orange. What's happened is the moon is really bright. So a photographer takes a really short exposure over here, even all the way to this part here. When there's any sunlight bouncing off it, the photographer takes a really short exposure, else it would saturate the image and it wouldn't look good. But once it's completely in the shadow, it's really dark. It's not completely dark as you might think. Some light does get scattered onto it, and I'll explain where that comes from in a second, but it's still very dark. So the photographer takes a much longer exposure, bringing more light in so you can see it. And that's what is printed here. If the exposure were the same length as the others, you wouldn't see anything. And that's kind of how the human eye works too. It adapts. If you're looking at something bright, the pupils shrink, you bring in less light. If you're looking at something dark, they expand, you bring in more light. So it naturally compensates. Now let's answer, where does this light come from? Put the dot cam back up. So let's see, here is Earth. The sun's over here, and it's casting a shadow like this. Moon's in the shadow. You might think it should be completely dark in there. We shouldn't be able to see anything. And that would be true, except we have an atmosphere. We have a really thin atmosphere hugging our surface. In fact, I've exaggerated how big it is in drawing that. It's really, really thin. But anyway, some of the light rays coming from the sun, just strike the Earth and that's it. But some of them skim through the atmosphere and get scattered. And some of that light gets scattered down onto the moon. And that's why we can see the moon during a lunar eclipse. It's scattered light coming from here and here and all points on this ring, perpendicular to the incoming light. So it gets illuminated from all angles. And one thing about light is blue light scatters more easily. So the blue scatters out like this, the red scatters less. So what hits the moon is predominantly red, because most of the blue has been lost. That's why these eclipses look red in color. In fact, they're getting redder with time, which is an interesting tidbit. As our atmosphere gets more polluted, there are more particulates up there that scatter out even more of the blue light, making the moon a little bit dimmer during eclipses and a little bit redder than they were historically. Just a little fun fact. And the other weird thing about this is we're used to looking at the moon directly illuminated by the sun. But now, in this case, it's illuminated coming in from the sides, from all sides. So it's a weird kind of illumination, and it makes the moon look three-dimensional during a total eclipse. This is a real picture taken by actually someone I knew in grad school. He does some amateur photometry for fun. Since it's being illuminated from different sides, it actually looks like a ball floating out there in space instead of a disk just kind of pasted to the sky. And if you do this, it's particularly good if you're looking at it with binoculars. So next time you have a total lunar eclipse, take out some binoculars. You don't need a telescope or anything and look at it. And it's unsettling because, again, we're used to looking at this disk. It looks kind of like the Death Star just floating up there, a three-dimensional sphere floating above you. So worth testing out. Let's see, I still have 7 minutes, looking great. So let's move over to solar eclipses. What's in the middle for a solar eclipse?
Moon.
The moon. So here's a solar eclipse configuration. Again, nothing to scale. We have the sun, we have the moon casting its shadow on the earth. The moon is small, the earth is big, so it casts just a spot on the earth. Like during a lunar eclipse, the whole moon is in the shadow. During a solar eclipse, there's just a tiny shadow on the earth. And the earth is rotating, and the moon is moving too in its orbit. So that shadow, and here you can see this is an actual satellite image from space. There's a dark spot. It moves across the surface at a pretty good pace. It's about, if you're in the path of totality, depending on the geometry of it all, you'll be in darkness for between 4 and 7 minutes. A little bit less if you're not directly in the center of the path. But 4 to 7 minutes of darkness. How many of you saw the eclipse back in 2017? And how many of you saw it in totality?
I did.
Pretty awesome, isn't it, right? I never saw one before that, and I drove over to Tennessee and found a spot right in the path and watched it. It was really amazing. It's surreal. That's the part I didn't appreciate. I've seen lots of pictures of eclipses, but you're in this spot of darkness. The surrounding area is still bright. You look off on the horizon and it's bright. It's like twilight, but not on one side of the sky. It's twilight 360 degrees around you, which doesn't feel right. Then you look up in the sky and the sun's gone. That's weird. But around it, you see the corona. You see, I'll pop ahead a few images. These are pictures from 2017. The corona is always there. It's just much fainter than the sun, so you normally don't see it. But you block the photosphere of the sun, you can see the corona. And you look at these pictures, and it looks really big, but it's just this, when you're out there, it's just this tiny thing. Half a degree, you can cover it with your thumb. Just up there, this dark circle in the sky, the missing sky, it's like, it's a nerdy reference, but the Eye of Sauron from Lord of the Rings, just floating up there, looking down upon you, wreathed in flame. And anyway, a really cool experience. If you missed it, another one's coming. I think it's in 2024 between Texas and Maine. I forget which direction it's going, but you may want to try to catch it then. I think it's in April that year. Okay, so let's look at some geometries here. Different types of eclipses. Here we have, the sun's off to the left. Here we have the moon. It's casting a shadow. And this dark spot is called the, let me write down some terms actually on the dot cam. And to save time, I wrote this in the previous section. If it's a total eclipse, it's called an umbral eclipse. Partial, it's called penumbral. And we'll also encounter annulars, which are a special type of partial. So let's look at this diagram here. Let's start with the totals. You got to be in this cone, this narrowing cone, for a total eclipse. And there it is. And then you can see the fainter corona because your eyes can adapt and see that. But it's a small circle. If you go a little bit higher, the moon can block part of the sun, but not all the sun. Some of the sun's light will come across over the top here. Moon blocks the bottom or something like that, and you get a partial. And that's a much bigger circle. So totals are pretty rare. For a given spot on the planet, you gotta wait decades for a total to come through. But partials, I guarantee you've been outside during plenty of partials and didn't even realize it. And it's because the eye is a powers of 10 device. The eye can notice things if it's 10 times fainter, 10 times brighter, but if you block half the sun or even 3/4 the sun, you don't really realize it. It's kind of like a thin cloud passed overhead. You just ignore it. The only way you'd know about a partial is if you read about it in the news beforehand. Normally, that doesn't come out until the day of. So you read about it in the news in the morning, you're like, oh, I'd like to see that. What can I do? And you may still have your eclipse glasses from 2017, but if not, you need a special kind of welder's glass. You'll never find that in time. So I'm going to show you 2 inexpensive ways to pull it off. This way, I've done it before, and the side benefit is you look really cool when you're doing it. But you get a box, and just poke a little hole in the back side. You may want to actually cut out a square and put a piece of paper and poke the hole so it's a nice clean hole. And you're making a pinhole camera. Put another piece of paper on the inside, and the light will cast down, and you'll be able to watch the sun and the part that's carved out by the moon. So I've tried this and it works. You just got to make sure you don't stick your head so far in you block the path of the light. And if you can't scrounge together a cardboard box in time, just stand under a tree. You've stand under trees before and looked up and you see all the little pinholes of light. Well, they act as pinhole cameras, and they'll cast shadows or light shadows of the sun. And you can see, if you look carefully, all these little crescents all over the place. And you might have noticed this back in 2017. If you knew during the eclipse, or actually even before or after it, just to go stand under a tree, look at the ground, this is what you would have seen. And I've seen this before a couple of times, actually. So that works. And here's just a, just so we end at the same place as the other class. Here's, again, the same idea. It's a time sequence where for that middle image, the photographer took a longer exposure to bring out the corona so you can see it better. Okay, so that's it for today. I'll stick around for questions. And no class on Monday, so we'll pick up on Wednesday. Homework will be due on Friday. So thank you very much.
Thank you.
Thank you, Doctor.
Thank you.
Thank you.
Thank you.
Thank you.
Thanks. Thank you. Wait, why don't we have class on Monday?
It's something the chancellor announced just last night. It's for people, to give people time to move out. Monday and Tuesday, classes are canceled.
Sweet.
Yep. We're all
Thank
required,
you.
we're required to make it up somehow, though, because
Okay.
Yeah, they're basically like, you get the time off, but
and that's because we're an accredited university, which means you must have a certain amount of class time. And I'm just going to assign a video of a standalone lecture to make up for it.
Thank you.
Could you go back to your notes on the umbral eclipse and like what the rest of the terms were?
Oh, so the dot cam, yep. Umbral means total. Penumbral means partial, so you know what those terms mean. And annular, we haven't explained it yet, but I will next time. It's a type of partial where the moon is perfectly aligned with the sun, but it doesn't cover the whole thing, so it leaves a ring around it.
Awesome. Thank you.
Sure.
So I remember I saw the eclipse in 2017, and maybe right before it, it looked like there was sunset on all horizons.
Yes.
What causes that?
So the dark spot that you're standing in is not very big. And so if you look off in the horizon, that part is still illuminated. And so it looks like sunset, but all around. It's because those parts are still in sunlight. Only you are not.
Gotcha. Thank you.
Yep. It's a weird feeling.
When are we going to have like our first assessment or quiz on chapter 1?
That would be lesson 1, homework 1. And I think I mentioned, I can't remember between the 2 classes, but since I had to postpone, since there's no class on Monday, I've pushed it to Friday. Did I mention that in class today?
For the homework, yeah, but
Yeah.
that's not like, there aren't any tests scheduled, are there?
So there are going to be 2 midterms and a final. The first midterm is after lesson 3, after homework 3. The second one's after homework 6, and the final's after homework 9.
Okay, so we only need to worry about the homework between the first midterm?
Yeah, until the first midterm, you have these 3 homeworks. And again, you have 3 shots on each question. So I expect everyone to ace or nearly ace it. It's not going to be very useful for me to assign grades, but it's useful for you to get ready for the exam.
Okay.
Of course, if you skip the homework, that will impact your grade.
Yeah, okay, thank you.
So real quick, our next homework is on the 28th, correct? Like the first
Yep.
homework soon?
It's
Okay.
now on the 28th, much later than I wanted, but that's just where we stand.
Okay, and another quick question. Okay, so with the with the synodic phases, so like the reason that the time is shorter, is that because like I know how you were saying like the Earth, it kind of has like the degree change, but so why does the moon have that time change as well?
Yeah, so it's because the Earth-Moon system is orbiting around the sun. If we would stay put, if we just stayed here the entire time, then one sidereal month would be the same as one synodic month. The time to go completely around with respect to the stars would be the same as the time to go completely around with respect to the sun. But once we go around with respect to the stars, we're actually over here because the whole Earth-Moon system has shifted upwards. So you can see this angle is the same as that angle. So Earth, Moon, some distant star, Earth, Moon, same star off in that direction. So it only takes 27.3 days for the moon to get back to the same constellation in the sky. But since we have shifted Earth and the moon with respect to the sun, the moon's going to have to orbit a little bit more to get between us again. And that's when you're back to the new phase.
Okay, so it's just like kind of like a game of catch up continuously.
Yep. So
All right,
synodic
thank
is a
you.
little bit longer. Okay. Anyone else?
Do we know how long it takes for objects like the moon or like any other objects really to become tidally locked with their planet?
I don't have the answer off the top of my head, but my understanding is it happens pretty quickly. In astronomical terms, which could be, pretty quickly in astronomical terms could be thousands or even hundreds of thousands of years. But the solar system's been around 4.6 billion. So even if it took 1 million years, that's a short time scale, but I think it's faster than that.
Okay, that's actually really cool. And also, what was the thing? My speakers weren't working at the beginning of class. Did you get the grant or something, or what was that?
Yeah. I got a $2 million grant right before class, so I was just excited about that, and announced it mostly get it out of my head so I can focus on the class for 50 minutes. But now I'm going to go back and think about the proposal.
That's really cool.
Congratulations.
Thank you. All right, if there's nothing else.
Have a good one.
You too.